This lecture is going to be our first of probably about 3 lectures on compact sets in a metric space. In this lesson, what we're going to talk about is the definition of a compact set, which involves the notion of an open cover. So we're going to start here. In a metric space, given some set A, we say an open cover of A is a collection of open sets whose union contains A. I denote this collection of open sets as U sub lambda, where each term here is an open set. So each member of the set is an open set. And then I index these as lambda in lambda, so little lambda and big lambda, to indicate that I don't know what the collection looks like. It could be a finite collection. Maybe I could call this U sub 1, U sub 2, U sub 3. And with those 3 open sets, when I take their union, every term in A is found in their union. More realistically, it's probably an infinite collection. And even if I know it's infinite, I still don't really know how to index them because it could be something like U sub n for all n in the natural numbers. So I could have some countable collection of open sets covering A. Or it could be an uncountable collection. Maybe for every real number, I have an associated open set. Let's talk a little bit about this notion of covering A. So formally, we say their union contains A, or in other words, A is a subset of the union over this collection of U sub lambda. This is set containment. So this means every X in A can be found in at least one of these open sets from the collection. Visually, I like to imagine this as like A is a set. So here's a set. And I have this way of thinking of these open sets as like little blankets, or sometimes I call them pancakes. And they are just, open sets covering A. So I think it's helpful to kind of literally picture them as covering the set, like a blanket. In this picture, I'm trying to emphasize with the one I just drew. Okay, I'll stop there because it's getting worse. What I'm trying to emphasize here is that the open sets covering A can also cover some of A complement. Maybe they cover the entire metric space. So it's not saying that this collection of open sets exclusively covers A, but together, this family of pancakes I just sketched covers the set A. Okay. Let's look at this example down here. So I have a collection of open intervals. I have an open interval for every single natural number. So the first one, maybe I'll write them out. U sub 1 is the open interval from -1 to 1. And then U sub 2 is the open interval from 0 to 2. U sub 3 from, don't worry, I'm not going to write all of them, but from 1 to 3. And then if I kept going, I would get to, let's say, U sub 11, which is going to be from 9 to 11. And then I have infinitely more beyond that. But together, all of these cover the closed interval from 0 to 10. So that's what this example is saying, is that this family of open sets, infinitely many open sets, when you take the union, 0 to 10 is a subset of that union. Now, looking at this, you might think, hey, this seems really like extraneous over here. And that is the case. I actually only need this first, say, 11 sets from this infinite family to cover the closed interval from 0 to 10. And this idea of throwing out most of them and reducing from an infinite collection down to just a finite subcollection is really key to understanding compact sets. So let me take a moment now. I'm going to switch slides, finish writing this down if you'd like, and then we will keep looking at examples before we define compact sets. In the previous example, when I threw out most of the collection of open sets and said, hey, we only needed the first 11, what we were doing was passing from an original open cover of a set down to what's called a finite subcover. So given an open cover of a set in a metric space, typically you want to imagine that it's an infinite collection of open sets. A finite subcover is just a finite subcollection of those open sets, which still covers A. So stated precisely, A is contained in this union, where this is the union of only finitely many open sets, and that is a subset of the original open cover. So as we looked at the open cover that we started with was like full of extra sets we didn't need. All we needed were U1 through U11. Let's now look at an open cover which might not allow for a finite subcover. In this example, consider that we are working on the real number line with the set which looks like the open interval from 0 to 1. I propose this as an open cover of the set, although we will verify that. For each x in A, design an open interval, which we will denote as u sub x, consisting of the points between x over 2 and 1. Is this an open cover of the set A, and does it yield a finite subcover? Okay, so let's think about what these open sets look like. Let me just write down an example. U sub 1/2. Here, x is 1/2, which means I'm going to write down the open interval from 1/2 divided by 2, so a quarter, to 1. Okay, each of these is an open set, and together they are going to cover A, because every single entry in A, every element in A, is at least in its own. In fact, it's in many more, but we can say that every x in A belongs to u sub x. Let me write this down. So the answer to the first question is yes, because each u sub x is open, and each x from the set that we're trying to cover belongs to at least one of them. It belongs to its own. All right, is in its own u sub x. This is an open cover of A. That's all you have to check to show that a cover is an open cover. Does it consist of open sets? Yes. And does it truly cover A? So is every point in A in at least one of the open sets? This is an uncountable collection of open sets because A is uncountable, and I have one for every single element in A. Can we reduce down to a finite subcover? So from this uncountable collection of open sets, is it possibly the case that we only need finitely many? Try to experiment with this. So from this starting open cover, imagine what a finite subcover would look like. When experimenting with these sets, you may have realized that everything covered by u sub 1/2 is also covered by u sub 1/3, so we don't need u sub 1/2. Certainly, we can throw away a lot of these sets and still cover A, but we cannot reduce all the way down to a finite subcover. So the second answer is no. We always will need infinitely many of this family in order to cover the open interval from 0 to 1. I think the cleanest way to show this is to use contradiction. So I will write, for the sake of contradiction. So SOC means for the sake of contradiction. Suppose that there is a finite subcover. What I'm going to do is provide a set of these open intervals, and I'll use the subscripts to kind of index through this finite set. So we'll say u sub x1, u sub x2, all the way through u sub x capital N, where the idea is that I have 1, 2, all the way through capital N, maybe that's 50, like members of my finite subcover. Okay, so suppose that this is a finite subcover. Well, each of these sets corresponds to a choice of point from A. So each of these sets is defined in terms of x1, x2, all the way through xn. That is a finite set of points from the open interval from 0 to 1, which means there is a set minimum. Okay. Suppose, we'll keep supposing, that you could even say that you ordered these. So x1 is less than x2 is less than xn. And that is the route I will take. Now I'll just say x sub j. Sorry, there are different ways that you could write this down, but I'm just going to go with a kind of choice here. X sub j is the minimum of this finite set of anchor points. We do not always know what a finite subcover would actually look like. We might not have like this kind of recipe for how to design this open cover. But in this particular example, I have a formula for these sets. And through examining this formula, I can tell you that the union of this finite collection of open sets is going to be the same as just U sub xj. Since U sub xk is a subset of U sub xj for all of the other anchor points. Here I'm referring specifically to these points. So since all of the others are a subset of U sub xj, because that's the one that kind of cuts us most to the left, the union, sorry, it's supposed to be a union symbol, the union from I equals 1 through n of these sets, U sub xi, is actually equal to just U sub xj, which is actually equal to xj over 2 through 1. So it's like by only taking finitely many, we cut maybe close to the left side of this domain, but we're not going to get all the way down to 0. We're not going to cover the points between 0 and x sub j over 2. Thus, we do not cover anything between 0 and xj over 2. All right, so this is often the strategy when you know that there is no finite subcover, is to imagine that there is one and then show that it fails. In this case, we just can't approach 0 with only finitely many of these sets. All right, I hope you have a good feel now for what it means to pass from an open cover to a finite subcover, because that's going to be the key notion behind the definition of a compact set. Okay, we are now ready to give the definition of a compact set. We say a set A in a metric space is compact if every single possible open cover of A must yield a finite subcover. So it's not enough to say that there exists an open cover of A which yields a finite subcover. You need it to be true for every single one. That means that the open interval from 0 to 1 that we were just looking at is not a compact set, because we were actually analyzing an open cover which did not yield a finite subcover. All right, this definition can be hard to work with because you can't really picture every possible way that you can cover a set with a family of open sets. So sometimes I think it's easier to start with sets which are not compact and create open covers of them which do not yield finite subcovers. We just did that with the open interval from 0 to 1. Now we're going to do it with integers, the Archimedean set, and also rational numbers between 0 and 5. Take a moment, pause, and see if you can come up with an open cover of each of these sets which does not yield a finite subcover. So you will always need infinitely many members from your collection of open sets to cover each of the sets in question. All right, let's go through examples for each of these. I'm going to propose open covers which yield no finite subcover. Yours might be different, but hopefully they're correct. You think about integers. This is a family of discrete isolated points on R. I can come up with a few different variations on this. What I'm going to do is take each integer and enclose it in an open interval of radius 1/2. Okay, each one of these open intervals is an open interval, so it's a family of open sets. Every single integer is found in its own neighborhood, so it covers integers. But we can't pass down to a finite subcover because we need all of them to cover every integer, and that's an infinite set. So let me write out, I think I will just write the description of the set. So around each integer, draw a neighborhood of radius 1/2. You could go all the way up to radius 1 here. So with this notation, this description here is the U sub k. We have a bijection between these open sets and each integer, the family of integers. So you can't throw out a single one of these because when you do, you will fail to cover the integer at its center. So this is an infinite open cover of the family of integers that yields no finite subcover. The Archimedean set, we could do something similar because like integers, the Archimedean set, if you look at the points in it, it's a family of isolated discrete points. So you could embed each one in an open interval. You would have to shrink them as you travel to the left, as you get closer and closer to zero, but it's still possible. Another option, just to give you some variety, would be to say, how about 1 over n plus 1 through 1? Actually, I have to cover 1, so how about through 2? I chose a denominator of 1 over n plus 1 because I want this to cover the nth, like 1 over n. So I'm going to think of this as like u sub n. Every single point of the form 1 over n is in its u sub n. So the Archimedean set is being covered by this infinite collection. They are all open intervals, so it's an open cover. But kind of like the example we were just looking at with the open set from 0 to 1, I cannot take only finitely many of these and still cover the Archimedean set, because if I reduce down to a finite subcover, there's going to be like a left side that's going to stop us well short of 0, and we'll be failing to cover all of the Archimedean points between 0 and wherever we cut off on the left. So I'm not going to write that down because it's almost the same as the example we just did. The third example is probably the hardest if you haven't seen this kind of construction before. What we have are rationals between 0 and 5. How do you start to cover this? I mean, you could do open intervals, but I'm going to cover it in a way which I will recognize yields no finite subcover. Here's the idea. I know that every real number is an accumulation point for the set of rationals. So let me take a real number between 0 and 5, which is an accumulation point for rationals, but which is not rational. So basically, I'm going to identify an irrational number between 0 and 5. How about pi? So for each n, let u sub n be the complement of a closed interval. I'm going to do, I could do pi minus 1 over n through pi plus 1 over n. That's a closed interval, so to form a family of open sets, I will take its complement. And then our cover is going to be u sub n for all natural numbers. This is a little stranger than what we've seen so far, so let me illustrate what's going on. Imagine here's 0, here's 5, here's pi. The first one looks like pi minus 1 through pi plus 1, the exterior of that. So that would be like, let's say here to here, I'm covering to the left and to the right. Okay, so this is one version of a u sub n, maybe u sub 1. But u sub 2 would look like here and here, the exterior of that. So I've slid a little closer to pi and I'm covering away like that. So we could keep cutting closer and closer to pi. And as we do, we will eventually cover every rational number. In fact, if you look at the union here over all natural numbers, the union of all of these is going to be the entire real line except for pi. Pi never gets covered. Okay, so this is a family of open sets covering really all of the rationals, but particularly the rationals between 0 and 5. That was our goal. However, I cannot reduce this infinite cover down to a finite subcover for reasons similar to this one. If I tried to say that there was some maximal index in a finite subcover, what we would be doing is creating a little window around pi that doesn't get covered. So if I stopped it, I guess it would actually be, I should probably have an open, but what I'm trying to really emphasize is that my picture's getting worse and worse, but if we only took finitely many members of this open cover, we are not going to get all the way to pi. We're going to leave some rationals to the left and to the right of pi, which are not going to be covered by finite subcover. So this is an open cover of our starting set, which yields no finite subcover. That's what we saw for all three examples. So none of these examples are compact sets. Before we move on, because I have two results I want us to show, I want to mention now that there's a kind of pattern to how I created the open covers that yielded no finite subcover for this example, and also actually the open interval from 0 to 1. Each of these covers was based on creating a cover kind of based off of an accumulation point that didn't belong to the set, if that makes sense. So with the open interval from 0 to 1, I was cutting closer and closer to 0. But if I had to stop somewhere, because 0 is an accumulation point, there would be points from my set I wouldn't be covering. That's the same thing happening here. So here we're cutting closer and closer to the accumulation point at 0. But if we ever stop that process with only finitely many sets, we would fail to be covering the members of the Archimedean set, which are really close to 0, because 0 is an accumulation point for the set. Here, pi is an accumulation point for the rational, so I know there are rationals arbitrarily close to it. So it's like I created an open cover based on this idea of like approaching this accumulation point. And then when I try to stop that process after only finitely many sets, we're not going to pick up the members of the set which are even closer to the accumulation point. Okay, I'm mentioning this partly to teach you how to construct these counterexamples to show that a set is not compact. And I'm also pointing out here that if your set has an accumulation point which lives in the complement, then you're going to be able to do this kind of process. So we are never going to say that a set is compact if its complement contains an accumulation point. In other words, if a set is not closed, it will not be compact. All right, in a moment, I'm going to prove two results before we wrap up this lesson. One is related to what I was just saying. And we are not done with compact sets because there's more to say. And in particular, I've given you examples of sets which are not compact, but I haven't really talked too much about sets which are compact because I think this definition is hard to visualize. So the goal of the next few lectures is to keep building up our understanding of compact sets. I'm not ready to wrap this one up though, because I have two kind of broad statements that I would like to leave you with. I think I said I had a pair of statements to prove. I have three. So these two go together, and then we will talk more about the relationship between compact sets and closed sets. Okay, I said I hadn't given you any explicit examples of compact sets. Let me do so now. Any finite set in any metric space is compact. So if you only have 15 elements in a set, it's compact. And then the second one is saying any infinite set in a discrete metric space, so here the metric is given, is not compact. Take a moment for the first one. If I want to argue that any finite set is compact, I have to be able to conclude that any open cover of a finite set must yield a finite subcover. Why is that necessarily true? Here's the idea. Maybe I start with an uncountable family of open sets to cover capital N terms. Every single element in this finite set must be covered. So what you do is you just say, okay, pick a set that covers x sub 1. Maybe it covers the rest of it, but let's just cover x sub 1. Then pick a set that covers x sub 2. Then pick a set that covers all the way through x sub n. So you might end up picking a set more than once, but you need no more than capital N sets, one for each of these, to create a finite subcover. I can probably write that down. I'm going to do it pretty concisely. Suppose this is some collection of open sets covering this finite set. I'm going to use this subscripting here to kind of indicate how the finite subcover should be constructed. Then U sub x1, sorry, I'm passing from lambdas to a different subscripting, chosen so that x sub I is in uxi, is a finite subcover. Okay, so that's the idea. To cover 8 points, you need no more than 8 sets, one for each. It's quite possible for an infinite set to be compact in, say, a Euclidean metric space. That's totally fine. But an infinite set in a discrete metric space is never compact. Kind of like the three examples we were just looking at, if you want to show that a set is not compact, all you have to do is come up with one open cover of that set that yields no finite subcover. That's actually very easy to do in a discrete metric space because every set is open, including singleton elements. So imagine that capital A is an infinite set in a discrete metric space, and let my open cover be singletons. I'm not going to write more. A singleton is not an open set on the, say, number line, but it is in a discrete metric space. So each of these is an open set. Every element in A is being covered by its own singleton cell. So we are providing an open cover of this set. But like our example with the integers, there's a bijection here between the elements of the set and the elements of the open cover. And in particular, I can't throw away a single one of these because then I would fail to cover something from A. So this is an infinite family of open sets, which yields no finite subcover. Okay, so I think all of the examples to this point have been on the number line. I wanted to mention this. This means that you can immediately determine whether or not a set in a discrete metric space is compact or not. It just depends on its cardinality. If it's finite, it's immediately compact because any finite set in any metric space is compact. If it's infinite, it's not compact. So determining whether or not a set is compact in a discrete metric space is not very fun. Or it is very fun, depending on how easy you want the question to be. All right, we have one more result to prove before we wrap up this lesson. All right, let's now prove a statement that I was alluding to earlier, which is that if a set in a metric space is compact, then it must be closed. The converse is not true. For example, the integers are a closed subset of the Euclidean real line, but they weren't compact. Okay, but this direction is true. So if a set is compact, then it is closed. Let me write the contrapositive. If a set is not closed, then it is not compact. So I'll just write not closed implies not compact. For two reasons, we are going to prove the contrapositive instead of the original statement. But both this and this are better, in my opinion. When you say that a set is not closed, you immediately gain a very specific piece of information, which is that there must be an accumulation point for the set in the complement. So you know an accumulation point exists in the complement. That's a very useful tool to have. And then I think it's easier to show that sets are not compact than to show that they are compact, at least with the open covers definition. And that's because if I can just generate one open cover of our set that yields no finite subcover, I'm done. So to show that something is not compact, you just need one cover, which yields no finite subcover. If I want to work with the idea of compactness, I have to consider like every possible open cover, and that's, I think, a little harder to do. Okay, so let's just jump right into this. We're going to assume that A is not closed. I will start off with like maybe the next sentence. Suppose there exists Y in a complement, which is an accumulation point of A. If you saw me hesitating, it's because if I were writing this on paper in a formal way, I would not use a quantifier like this. I would say, suppose there exists, and I would write it out much more nicely, but on the board, I have to use shorthand. Okay, so suppose that there's an accumulation point of A in a complement. We are going to design an open cover of A based on that point, just like we did when we proved that the set of rationals between 0 and 5 was not compact. I created an open cover by using pi and creating kind of exterior neighborhoods, like nested exterior neighborhoods. That's the idea. Create an open cover of A as follows. Let me write out the definition of the sets in my open cover, and then I'll sketch a picture. So for each natural number let u sub n be like an exterior neighborhood around y. So what I'm going to do is take the neighborhood of radius 1 over n, so I'll invert this, around y, and then I'm going to close that off so that when I take its complement, it's an open set. This is kind of a weird way of saying it's all of the points in the metric space whose distance to y is greater than 1 over n. All right, so what is this going to look like? Sketch the point y. Starting with n equals 1, radius 1 around y might look like this. It was supposed to be a perfect circle of radius 1. The closure of that neighborhood would be the solid disk of radius 1 around y. And then I'm going to take the complement of that. So that is this open exterior neighborhood around y. Okay, that was for n equals 1. And then for n equals 2, the radius is going to shrink from 1 to a half. So here is radius 1/2 centered at y. And then u sub 2, really, to go with 1/2, u sub 2 will be this exterior neighborhood. And I think you have the idea, but let me just keep going so I can use blue. U sub 3 will be the exterior, open exterior of the ball of radius 1/3 around y. Okay, so we have this nested family of exterior sets. Each one is open. And ultimately, we are going to cover A because as n grows to infinity, the radii are going to shrink inwards. If you take all of them, actually the only point in the metric space which won't be covered is y itself. That's okay because we know that y is not in A. So by covering everything except y, we cover A. All right, I think I'm not going to write out all of that. Let me just say, notice, leaving the reader to do quite a bit of work here. Notice the union of all of these is everything but y. Everything but y. So A is covered. It's an open cover of A. It's covering A, and each one is the complement of a closed set, so it's an open cover. The thought process here is exactly like when we tried to cover the open interval from 0 to 1, the Archimedean set, and that example with rational numbers. Imagine what would happen if instead of using an infinite family of these exterior neighborhoods to cover A, I only used finitely many. Let me give you a moment to pause because this is the end of this lesson and we've seen this idea a few times. See if you can work out what a finite subcover would have to look like. Okay, what I'm going to say is consider a finite subcollection. So consider u sub n1, u sub n2, all the way through. How about u sub n capital K? And since I have a finite set indexed with natural numbers, what I'm going to say is that these are ordered so that the n2s are in, or the n1 is less than n2 is less than nk. All right, indexed with n1 less than n2 less than nk. Indexed or ordered. That's fair because it's a finite set and their anchor points are natural numbers. All right, so this is what a finite subcollection would look like. The largest natural number found in the finite subcollection will define the smallest radius. So maybe that looks like this. Right? So actually, when I consider the covering by this finite subcollection, it's really equivalent to just the exterior neighborhood defined by this largest natural number from this set. Again, you don't always have a formulaic way of looking at the members of an open cover, but in this particular situation, we do. So given that we've seen this idea a few times, I'm just going to jump straight to like saying that. Notice, again, the reader is having to do a lot of noticing here, but I think I'm communicating it out loud. So notice that the union from I equals 1 through capital K of U sub ni is actually just U sub nk. And maybe I'll write that out now using the other way to describe this exterior neighborhood. So that is all of the points in the metric space whose distance to y is greater than 1 over n sub k. However, y is an accumulation point of A. That means that there are points from A in this neighborhood and they're not being covered. Let me see if I can squeeze that on here. But yeah, I think I can. So how about just the complement of that? I'm going to go back to kind of complementing things. U sub nk, I'll just say, hey, flip it, go inside. I don't care about the boundary. Just take the complement. Intersect A is non-empty since y is an accumulation point. Thus, there can be no finite subcover. Finite subcover, so A is not compact. Okay. This proof really illustrates or follows the examples that we saw earlier, where again, I constructed an open cover by kind of looking for an accumulation point in the complement. So I hope that this kind of underscores your understanding of those examples. Let me wrap up just by pointing out that both directions of the statement are useful. So if we know a set is compact, we know it's closed. But if you're looking at a set and you're trying to determine if it's compact or not, working directly with the definition of compactness can be challenging. However, if you could spot that it's not closed, then you're done. You know it's not compact. Revisiting, say, the Archimedean example, that set is not closed. 0 is an accumulation point in the complement. So we could have stopped there. We didn't need to come up with an open cover that yielded no finite subcover. So the Archimedean set, not closed, not compact. Any kind of subset of rational numbers, bounded or not, it was bounded in the example, but it doesn't have to be. Rationals are not closed, so not compact. The open interval from 0 to 1 is a subset of R, not closed, so it's not compact. All right, I hope this gave you a good starting point with compact sets. We have more to come.